Welcome everyone. This is the start of the talk for sure. And we are going to be looking at the third part of the Trinity Force of today's seminar. So we've had abstraction from Alex, resolutions from Daniel, and now we'll look at renormalization. This will be a fairly gentle introduction to statistical mechanics, which is the study of basically materials. And we're going to look at a quite advanced topic inside of it called renormalization. So the plan is to get through this gently and hopefully not too complicated. So the first question that renormalization and statistical mechanics in general, I suppose, deals with is why are materials simple when their parts are complex? So an example that I like is if you have a molecule of water, this is quite a complex system. For example, we know the angle between the hydrogens is about 105 degrees, and we know that the distance between the oxygen and the hydrogens is about 96 picometers, and then there's the valence electrons around the edge. So this is quite a complex object, but then all of a sudden when you get a bunch of them together and put them in a beaker, for example, you get water. And then I can understand pretty much everything I want to say about this water if I know its density rho, its viscosity nu, and its thermoconductivity kappa. And so the idea of renormalization is how can I start with something very complex like the water molecule and then just look at the liquid itself and I don't really care about all those details about the angle or the distance between the molecules at large. The second question is, how can materials change in nature discontinuously? And in the same analogy of this water, I could, for example, boil it, and that would be at a certain temperature, water boils, which I can't remember off the top of my head, but it goes from being in one state to a very different state rather quickly. And I guess I'll stick with the water analogy. Ice also melts at a certain temperature, where it goes from being a solid to a liquid. So these are two questions that we're going to look at today. Now, I want to outline the renormalization process. And maybe once we outline this, it might be a bit clearer what this connection is to abstraction. Sorry, am I in the way of the orb cam? Oh no. So we start with a microscopic theory. And in theory, this microscopic theory contains everything you want to know about the model. So you can keep the molecule of water as an example in your head. So we look at a lot of collections of small pulp molecules. And then we, in some sense, average out the smallest scale to get something bigger. So I'm not going to draw those dots again, but say we decide to connect, if we have a lattice, is the canonical example of perhaps magnets or anything really. And then we decide to average out the smaller scale by connecting these dots. And then we decide to treat each of these new blocks as its own point. So each dot here is really one of these blocks. So this is more or less what the renormalization process is in a picture. We start with something small, we connect dots pretty much, and then treat those new blocks as dots, and then we can repeat the process. So we can start with something tiny and then repeatedly renormalize the process until we get to something new. And this process is called coarse graining, with an A, not a U. Cool, so that's a lot of pictures. Let's write down some maths. So I said a lot about, well, not a lot, I said something about averaging over certain states. And so what are we averaging over? So we are averaging over the states that the system can be in, and we weight each state by the probability that it will be in that state. So for example, I'll just draw this over here. If you have a box of, say, a gas with them all flying around, you'd expect the gas to spread out fairly evenly, as opposed to the case where you have all the gas particles just like bunched up in the corner. This would be, you would probably weight this much less likely than the case where the gas spreads out inside the box, for example. So we'll denote a state with usually capital phi, but I'm going to use lowercase phi because it's quicker to write. And we'll say that the probability of any, didn't write this out very well, any state phi is given by something called either a Gibbs or a Boltzmann distribution, depending who you ask. I've always seen it in terms of Boltzmann, so I'll probably use that. But if I switch to Gibbs, I apologize. So this is the probability of state phi is e to the negative h of phi over t, and then we sum over all the states. Down here. So this h I've written is the Hamiltonian, which is the total energy of this certain state phi. T is the temperature. And then what we define this normalization constant at the bottom here, Z, we often call the partition function. And while it might just seem like a normalization constant, this is actually one of the most important quantities that we're going to care about, since it helps determine the probability of each state phi, and also we'll see later the free energy in most quantities of interest. It's quite common to introduce a parameter called beta, which is 1 over t, just so that then we can say the probability of a state is then just e to the minus beta h over z, of course. So this coarse graining procedure.
Sorry, do you mind if I just quickly ask a question?
Yeah, sure, go ahead.
Is t fixed or depending on phi?
T does not depend on phi. T is like the temperature of the system, and phi is like a state in that system. So I guess you could have like the gas in the box, and then phi would be, for example, actually I'll write this down. What I put it? Sorry. I put down the Apple Pencil and it just disappears into my white disk. So for example, you could have a gas in the box that I wrote before. So then phi would be just a collection of all the points in the box. So their positions and their velocities. Or you could have a magnet where it depends on some function m, which is the magnetism at each point. So phi, yeah, is independent of temperature.
Thanks.
No worries. So I think it's helpful to see what this coarse graining procedure looks like with a sample calculation. So when we're near a fixed point, which I haven't actually defined yet, but typically in this coarse graining procedure, it's common to split a state phi into a sort of larger scale state phi bar, and then a smaller scale state d phi. So what this might look like is if you have your function phi looks like that, then you can split that into the, oops, that's a line, into the big part phi bar, and then the small variation would just be like so the idea is that the red line plus the green line should equal the blue line, but I've drawn that kind of confusingly, sorry. So the coarse graining procedure, or the renormalization, would be that we want to have a map from our state phi to a new one, phi bar. So phi bar is considered big. So this is like the idea of what we drew before on the previous board of zooming out and repeatedly coarse graining. And we want, since we want to iterate this procedure, have the Hamiltonian and the probability of the state phi bar to look like the original one. So we want the probability of phi bar to look something like e to the minus h bar of phi bar over t for over z for some new Hamiltonian h bar. At least that's the hope. So I think an example of what this looks like is beneficial. So let's be explicit and say, what if we had our Hamiltonian was h equals, this is actually one from magnetism, but we'll pick a very simple example. So m is the magnetism strength of a magnet. Normally these m's will depend on x, but for this calculation we won't bother with that, and we'll just ignore any external magnets. But for the purpose of this, you can just treat this Hamiltonian as like just an example. And so then we'll say the probability of a state m will be roughly e to the minus h depending on m over t. So then we do what we did before, where we want to split our m into m bar plus some small varying delta m. And then what we'll do is we'll look at, so this implies, sorry, that m bar will be equal to, no, sorry, forget that. And the way that we remove this dependence on delta m is by summing over all possible delta m's. So that's where that sum came from, if you're wondering. And then this is what we'll define our e to the minus h bar of m bar to be. So now we want to find this Hamiltonian that looks like our old one, but in terms of new parameters, a bar, m bar, b bar. It's worth noting to make, oh, sorry, let's walk over here. Will that follow me? Yep. So we take our state delta m, so we know that we can expand this out as a Taylor series, which I will do in a second, but before I do that, we can expand it out as a function of delta m. And so on. And we'll note that since we're summing over all the delta m's, we can split the sum delta m into ones where the delta m's are positive and the delta m's are negative. And then we'll assume that since we're summing over all delta m's, we'll just assume there's an even number of both, assuming symmetry. But we can write the negative delta m's as positive ones if we bring the negative inside. And this will be true. So this will mean that any odd power, so for example, delta m or delta m cubed, will then just be equal to the sum over delta m greater than 0, delta m minus delta m to any odd power. So for the purpose of this calculation, where we sum over all these small variations, we're going to ignore all the odd powers of our Taylor series. And so what we're going to get in the end is that this sum up here will just equal delta m squared f2 on m bar plus delta m to the 4 f4 of m bar, and so plus smaller terms. And then we can bring this sum inside here and then treat these as just constants. So say a2 and a4. Okay, so we'll use that now. So going back to our state phi bar, this is equal to the sum over the delta m's e to the minus h on t, and then we can use Taylor series of the exponential. I'm also going to assume, sorry, I forgot to mention this, that t is considered very, very large. So typically when we do this type of calculation, it's near something called critical points, which is something like fixed points. And these usually occur in some cases when the temperature is very large, which for this case we'll assume it is. So we can then sub in our Hamiltonian. And then replace the m's here with m bar plus delta m as before. And then once we expand all this out, it will look like the sum over delta m's minus 1 over t, a m bar plus delta m squareds plus b, and then actually I won't do that, I'll do it here. Cool. And then what we're going to do as before is we're going to bring the sum inside through to the delta m's, and we'll just define some new variables to make this easier. So we'll call the sum over delta m's over constant a0, sum over delta m squareds, call that A2, and then similarly, sum over all delta m's to the M4 will be A4. So this leaves us with our new state to be A0 minus 1 over t Ooh, I'm getting a bit of lag on the iPad. Is that normal? Oh, I'm sure it's fine.
Yeah, you might have to turn the graphics quality down if it continues. I'm a bit confused. You had P of phi bar before, now it's P of M bar. Was it M bar the whole time?
Oh, sorry, I forgot to mention that. Phi, our state phi, is just going to be M. That's like the state that we're picking. Okay. Sorry. So like before I said we could have like phi, in the case of a gas, we have phi is a collection of the position and velocities inside a gas. And then in the case of a magnet, it's usually M, the magnetism of all the points X. But then we ignore the X dependency for this calculation. So phi is M, yeah.
Okay.
So yeah, you can basically treat phi and M as interchangeable for this calculation. So M bar is the new state that we care about. Yeah, the lag is getting worse. This is annoying. So once we then group this,
Yeah, so just take a moment, go into the Roblox settings on the iPad, go to graphics quality, and just turn it all the way down. You might have to put it from automatic to manual first.
Oh yeah. Yep, I did have to do that, thank you.
And you might want to put the brightness of the iPad screen down to about 1/3. Hopefully that helps.
Oh no, that seems to fix it.
Okay, great.
Thank you. Okay, so we've now expressed our new state in terms of these new constants, A2, A3, A2, A0, and A4. And now we want this Hamiltonian, remember, to look something like the old one, which was am squared plus bm to the 4. So we want to define new variables now, a and b, a bar and b bar, so that we'll get a Hamiltonian in terms of a bar, b bar, and m bar. And so I'm just going to pick the correct ones. So if we let a bar equal this, and then didn't leave enough space for b bar. What is it here?
I don't want to sound critical of your handwriting, but I just wanted to check that's a 6, right?
I don't think it's a... Yes, that is a 6.
Okay, I couldn't tell if it was maybe just a B or a delta, but it's a 6.
No, that is a 6. I blame all handwriting issues on the fact I've never written on an iPad before. Okay, so once we make this change, then our state becomes proportional to A0 minus 1 on t A2 plus A4b, and then that is just a constant, and that will be times 1 minus 1 on t A bar m bar squared b bar m to the 4. And then this is just call that c. This will just be c proportional to the exponential of minus h bar m bar over t. And so this is our now renormalized Hamiltonian, where we started with a Hamiltonian h in terms of m, and then we ended up with a new Hamiltonian h bar in terms of m bar. And the only thing that really we had to pay for that price to do this was to have this unknown constant at the front.
So
it's quite common in...
The c is that first factor.
Yeah, sorry, so this factor here is c. But this factor doesn't depend on a bar or m bar.
Sure.
And so as we repeatedly, which I'll show in a sec, as we repeatedly coarse grain, if we decide to do this again, it will just become...
Yeah, you say unknown, but you wrote down a formula for it. The hardly unknown.
Yes, it's known. It's right there. So, if we repeatedly coarse grain, and then we can see how changing these parameters, mapping A to A bar and B to B bar, say we start with A and B, start say over here in the AB plane, and then we redefine to A bar, B bar, and then that pushes our new variables to here, and then we repeat the process, and then we repeat it, and then we keep going until we eventually end up at this thing in the AB plane, which is a fixed point.
Can you move over
now,
a little bit to get the orb cam to these boards? Yeah.
Sorry. So if I was a better artist, this is the vector field, by the way. So you can imagine a lot of little blue arrows everywhere, sort of showing the direction of flow. So in this case, the vector field is pointing down that way. So you start in the AB plane somewhere, and then as you repeatedly coarse grain or repeatedly redefine the Hamiltonian, you're going to end up, typically in most realistic cases, you'll end up at some fixed point of the system. Now, you may have heard of something called renormalization group flow, or RG flow. And the RG flow is this line that we've created here. So that's the RG flow line. So then say, for example, you start out here with your parameters, then you're eventually going to flow towards the basin along the RG flow line. Oops, I didn't draw what I just said. You're supposed you would catch this line at some point and then follow it all the way down into the basin, and that's the RG flow. The reason that's called renormalization group flow, is the idea that if you coarse grain by a factor of say 2, and so you zoom out by 2, and then you coarse grain by a factor of 3 and zoom out by 3, it's the same thing as if you coarse grain by a factor of 6. So it's called a semi-group, meaning that you have the classic group multiplication. But it's not a proper group because inverses aren't guaranteed.
Yeah, information is lost under this process. Just to be clear, the RG step is from AB to A bar, B bar in your formulation. Right?
Yep. Yep, this is the renormalization step.
So regarding this constant C, correct me if I'm wrong, but so we could think of that as giving an additive factor inside the exponential, right? And that would just change the 0 point of the Hamiltonian. So it's an overall shift in the energy but which is kind of unobservable, which is why you're not caring about it. What matters is the coupling constants, the sort of constants that appear inside the polynomial h bar itself.
Yeah, you're completely correct. In fact, it's actually so, like you said, it's actually quite common to even start with a Hamiltonian plus plus the constant from the start, since it's going to pop anyway. So a lot of calculations I see, or you might see in the wild, is they'll start with a Hamiltonian and then just add their constant c to the at the beginning, since it's going to end up there at the end anyway.
Yeah, it's almost for various reasons, you kind of, it would be unusual to end up with a Hamiltonian after renormalization that didn't have some additive constant.
Yeah, exactly. So that's sort of the loose answer to the first question of what happens to materials as we zoom out. The second one was about phase transitions. So let's say we had a vector field that looks like this one, where we have our RG flow fixed points down here.
Wait,
so say if we start...
I don't buy what you've said so far as an answer to the first question. I hope
no,
Edmund
it's not like...
and Rowan are not going along either. So what you've described is renormalization, which so you've described coarse graining, and this example I think is a good one, but somehow the system looks as complicated as it did before renormalization, right? There's two parameters. It's the same class of models. In some sense, qualitatively, it's not like you have less things that you need to remember about the system. So what has this got to do at all with your first observation?
Yeah, sorry, I guess I misspoke. I didn't mean to say that I've answered why having complicated things together make it simpler. I guess what I meant to say was that we've shown how one might zoom out a little bit by an iterative step.
Right, and then
but
as a result of that, perhaps there's a second step where you extract some simpler description of the system. Yeah, I mean, I guess this example is, you could imagine perhaps that in this step where you did the coarse graining, in the limit, as you go from AB non-zero to AB 0, you could imagine that the description of the system at that fixed point is much simpler than its description away from the fixed point.
Yes, that is true. Because what I'm going to get to when this is more like a loosey. I guess maybe I shouldn't have done this in hindsight, like a loosey-goosey of what the renormalization process looks like. But you're right that once you get to a fixed point, if you then coarse grain and do another renormalization step, so say you had a fixed point T star, and then you did a renormalization function on that, you expect it to not change the fixed point. Like if I zoom out at a fixed point, I'm still at a fixed point. And there's a theorem that I can show later where all these fixed points are either, because of this fact, at 0 or infinity. And so I think what you're saying is right, that does make this like RG flow into these like simpler solution domains does occur.
Yeah, I think the description in terms of macroscopic coordinates is more is a kind of secondary issue, a bit outside what you've described so far. But yeah, continue with what you wanted to say.
Sorry, I wanted to ask a question. So this might be just a misunderstanding, but is the argument that macroscopic variable is whatever is lying on the submanifold, well, sub variety of fixed points, as in it's the, so let's say the AB get always converge to a submanifold of the red lines, and the red line, well, it's now a line, so instead of two-dimensional, it's one-dimensional.
Sorry to interrupt, Edmund, but suppose we added another axis here. Would that be kind of consistent with the picture you're drawing? Is that what you have in mind?
Sorry, is that for me or Edmund?
I was asking Edmund if this is what he's kind of describing.
I'm probably describing something in much higher dimensional, right? So Avogadro's number, 3 times Avogadro, 6 times Avogadro numbers of coordinates, and this you keep on doing this coarse graining procedure until you get down to 5 variables: pressure, volume, and so on. Is this saying that the 5 or so variables are coordinates on the 5-dimensional submanifold of this 10 to the 24 dimensional space? Is that completely off, completely wrong, or is that sometimes true?
I think you're correct in what you're saying, but I'm not confident.
I would be a bit more cautious than that. I don't know how to think about macroscopic thermodynamic coordinates as emerging in that way. It sounds kind of plausible, but it's
right.
I think the connection between the I think you'd have to, I mean, keep in mind that the renormalized theory knows everything about the system, even away from equilibrium, right? This is not this is not an equilibrium. This is a microscopic theory that has complete knowledge about the theory, about the system, right? Whereas the macroscopic thermodynamic coordinates, in principle, only characterize the system at equilibrium. So I think there's some connection between those two, but I think it can't be as straightforward as probably what you just described. I could be wrong, but I think that, I'm interested to understand better what that is, but I don't think I can tell that story right now.
Yep. Okay. Thank you.
Okay. So the other thing I wanted to show was how phase transitions can occur when, depending where you start in this constant plane. So for example, if you had a start with your AB there, then you would expect that your RG flow, or that your renormalization steps, would then follow this line down to that fixed point T star. Whereas if you instead, maybe you increase the temperature of your water until it boiled, or something similar, and then you shifted your starting point over here, then you would see that you would flow down to a very different fixed point, say T bar. So that's the overview of what, at least my introductory overview of what renormalization is, so that we can have this picture in our minds while we get into the nitty-gritty details of the one-dimensional Ising model. So the plan now is to spend some time looking at the Ising model. It's quite a well-studied example. It hasn't got any phase transitions, actually, at least in 1 dimensions, but nonetheless, it's still very instructive for seeing how this process can occur. In fact, since most of the examples that we'll be using is the Ising model, I think it's worth spending some time on it now to properly understand it before we renormalize it. So, the Hamiltonian for the Ising model.
Probably better to start on a new set of boards. You're going to run out with that one.
That's a good point. So we'll let omega denote a lattice. So in this one-dimensional case, it will just be a line of points. So what the one-dimensional Ising model is that it's a collection of spin sites, or like magnetism, along these sites here, where each node is said to have either spin up or spin down. And then there will be some strength between each of these magnets at each vertex, which, say if this is site I and this is site J, they might have some magnetic strength between them, Jij. So it's also quite common to consider an external magnetic field off the lattice, or the chain in this case, where, say, it's some magnet here, H, then each separate node will have its own specific magnetic strength it fields from this external magnet, depending on where it is along the lattice I. So you might expect as you move further away from this external magnet that your correlation with it goes down. So this is all the energy inside the system, the magnets on the lattice, and then the one external magnet off the lattice. And so the Hamiltonian of these spin sites, which is typically denoted as SI or sigma I, is equal to where each spin is either spin up or spin down, or plus or minus one. So the sum of all the configurations, which is typically denoted as the trace, will be summing over all of the spins in the Hamiltonian, which I may just write sum over all spins, Sn for short. And then using this notation, the partition function, which is the normalization constant for the probability state, will be equal to the trace of e to the negative beta, recall beta is 1 on t, of this Hamiltonian of the spins. It's probably also worth flagging some other important quantities, so that when I get to them and show them to you, you can be impressed. But like I said before, the partition function is quite important, since the free energy of a system is calculated directly from the partition function and the temperature. So this is the free energy, and then this is a known constant, quite a big one. It's like 10 to the 23 or something. And then the other quantity that is typically of interest is something called the bulking free energy, which is where we look at what happens when we take, in this case, the size of the lattice, n, to infinity. So these are two quantities that we'll calculate before we attempt to renormalize the Ising model. Okay, so there'll be two cases for doing this. Probably have time to do case one, since it's much easier than case two. So this one will be free boundary conditions, meaning that the lattice is just going to be a straight line of n nodes. each with either spin up or spin down. And then we're going to assume that the strength between all of them is j, so it won't depend on I or j, where the nodes are. And we won't have an external magnet for this one. So this simplifies the Hamiltonian quite dramatically. So then h will just be negative j. Oh, and it's also worth mentioning that in this case, we're only going to assume that each spin site interacts with its nearest neighbor, meaning that the second spin site only interacts with the first one and the third one, and the third one only interacts with the second and the fourth, and so on. So this average sum over ij up to n of omega will be just the notation to say that we're only going to sum over sites that are nearest neighbors. And so we can rewrite Sij as Si plus 1. So using this, the partition function is therefore going to be this. And we're actually going to define a constant j over t and call that k. So that will just be k, sum from I to n minus 1 si plus 1. Cool. So the way that we're going to derive what this looks like explicitly is we're going to use something called the recursion method. So now we're going to ask what happens if we were to add, say, another spin site on the n, an n plus 1 node. And how would that change the partition function? So now we'll say it's a function of k. So that would be k, s1, s2, all the way up to sn minus 1, sn, and then we're going to multiply that by e to the k. Oh, sorry, this should be an n plus 1. Okay, now, since S, this is the quantity we added at the end in the recursive step. That's just going to be equal to e to the k sn plus e to the minus k sn. So we just pick sn plus 1 to be plus or minus 1. And then this is equal to 2 cosh of k sn. And then since Sn is just either plus or minus 1, and this is an even function, we can just rewrite this as 2 cosh of k. So therefore, we'll get Sn plus 1 of k. Oh, sorry, thank you. Is equal to 2 cosh times Zn of k. And so then we can just recursively repeat this process until we get down to Z1, 2 cosh of k to the n minus 1. And Z1 is quite simple. It's just going to be the sum over the S1 nodes of the exponential of 0. So that just equals 2. And so therefore, we get left with Sn is just equal to 2 times 2 cosh of k to the n minus 1. And k is, remember, the strength between each nodes divided by the temperature. And so then using this partition function, we can then substitute it into the free energy, and we'll get this. And then really quick before I finish, from this expression of the free energy, if we then massage it a little bit, we can then pull the n-1 down the front and then split the multiplication in the logarithm to get minus kBt log of 2 minus kb.
It's a bit confusing. You're missing a bracket in the logarithm, so maybe it's not so easy to see that it's inside the logarithm.
Oh, sorry. Yep, my mistake. Okay, hopefully that makes it clearer. And then that second term is times the logarithm of 2 cosh k. So then if we take the bulking energy of this, which is the limit as n goes to infinity of 1 over n of f, we will get left with simply negative kb of t log of 2 cosh j over kbt. And so what this looks like, if we decide to graph the bulking energy as a function of the temperature, is that it will look just like a straight line going straight down. Well, actually, I don't know if it's a straight line technically, but it looks pretty close to one. And so we can see that we won't get any phase transition. It's an analytic function of t, as long as t is not 0. So that's the free case, which is the simpler one. I guess
Maybe you can say a bit about what's the significance of this observation? What are you doing by computing the free energy? What have you shown?
So calculating the partition function will make the renormalization of the Ising model a bit easier later on. So by calculating the free energy, we can see that since as the limit as n goes to infinity, so say if we added in an n+1 node and then kept adding them in and went to infinity, then we aren't going to have a phase transition, which is what we looked at over before, where we might expect in the renormalization process to discontinuously like break symmetry or shift points. So that won't, for this hysteresis won't happen in the one-dimensional Ising case, since the free energy is analytic.
Okay.
Does that answer your question?
Yeah, thanks.
All right, I guess I'll leave it there. And then for next time, we'll solve the case with the periodic boundary conditions and then renormalize the Ising model. And then hopefully with enough time, we can use that as a springboard to develop some theory about the scaling hypothesis.
Cool, thanks, Ben. I'll just add for Alexander that we've solved it. All the problems are resolved now. Ben has answered all our questions about how these three vertices of the Trinity fit together. But now we're going to leave and you'll just have to figure it out from the boards.
Yeah, and there's no YouTube video to watch it later.
Yeah, any questions for Ben?